Today we'll be starting with a new topic, which is transformers, right? So, transformers. Now, these are electrical devices which work on the concept of electromagnetic induction, right? So, electromagnetic induction. What is induction, right? If you remember, we talked about induction in electrostatics, right? This is the induced uh, charges that we get from one to the other without having a physical contact, right? So if we talked about electromagnetic induction, for this we have a particular device that we call as a transformer. What it does, that it converts or transfers electrical energy without electrical connection, right? Direct electrical connection. So for this, what we're going to have is we're going to have a primary coil, right? Let's say we have one solenoid, right? Like this, right? We're going to call this as primary coil. Why the primary coil? Because this is where the current is coming in, right? This is the primary coil. We need to have an AC power in here, right? AC power and DC power, we're going to talk about this as well, right? We have briefly talked about it, but today we're going to get into the real purpose of why we use AC and DC, right? This is the secondary coil for you, which has less number of turns for us, right? So again, let me just draw this because it tries to annotate my drawing very quickly, right? So over here, we're going to attach a voltmeter, right? So we're going to term this as primary coil, and the other one we're going to term as secondary coil, right? Now, as you can see that these two coils are not joined together. They have no link, no direct connection to one another, right? So how is electrical energy transferred from one to the other? Is a simple fact that you do understand that there's going to be a magnetic field created by this one coil over here, right? So we're going to have the magnetic field being created, right, by one coil, and there it convert into a circle, right? I need ovals over here, right? So we see that the magnetic field of the first coil is going to cut through the magnetic field or the second coil, right? So that is going to produce a flux change over here, right? And since this magnetic field is alternating, right? This is AC power, right? AC supply. That means the magnetic field will be switching off, right? So it will be going back and forth. It will switch over, right? Due to the alternating current. That will cause this needle to have an alternating output as well, right? So we'll see that the voltage in this one is going to vary like this, right? So let's say this is V positive voltage, and this is negative voltage. We'll see that the power over here is going to be alternating, right? This is called the alternating current, right? Where the power can alternate between the positive and the negative. Now, why we use AC for induction, right? Why we need AC, right? Because AC power supply is going to induce a change in flux, right? So if you remember induction, right? Induction of static charge. Over there, we got a static charge induced, but the static charge was not moving because there was a fixed field. Now, if you want the charges to move, we want to have a flux change, right? So we're going to say that induction depends upon flux change, right? Now let's define the term what is flux change, right? Flux change is basically the change in magnetic field, right? So changing magnetic field is called flux change, right? Changing magnetic field is called the flux change, or whenever the value we say that the delta B is equal to phi. Phi is just a representative of delta B, or the change in magnetic field strength, right? So you want the magnetic field to change or alter for you to make electrical current for you, right? In other words, we want to have changing magnetic field through the secondary coil so that it starts receiving current, right? It will start generating current due to the changes in magnetic field. Now keep in mind, it's the same idea as that of this one, right? The motor effect. It's the opposite of the motor effect. Now in the motor effect, we said that whenever you give electrical current, right, it creates its own magnetic field, and then as a result you get a force, right? Because it is placed inside another magnetic field. Now keep in mind, if you change the magnetic field here, and there is a force applied, right? You move this conductor back and forth without applying electrical field, right? So let's say if I remove this from here and attach a voltmeter across this, right, and move this rod, this copper pipe over here, right, we're going to see some voltage is being generated, right? So every time I move it in one direction, I'll see the needle moving in one direction, right? This is called electrical induction. This is called the Faraday's law. Okay, so for Faraday's law, let me just show you a little bit of a simulation, right? For this, we can go to FET simulation, and we can have a look over there on one of those simulations, right? That's called the Faraday's law, right? So motion, this sound waves, heat, electrical, right? So this is the Faraday's law, right? A generator, how does a generator work, right? And again, we're going to have a detailed version of this, right? So three simulations that are there, right? First, the Faraday law, how the Faraday law actually works for you, right? We're going to have a look at this. So we're going to start with a pickup coil, right? Now, if I take this magnet, I move this. So you see that the electrons inside this are getting repelled, right? Keep in mind, the electrons are also charged particles, right? So they have their own fields around them. If you know electric field, right? So that electric field is going to get repelled or attracted depending upon the polarity of this magnet. So if I move the magnet faster, you see that more of the voltage is generated, and if I move the magnet slowly, then the repulsion effect is slow. So the electrons will move slower. Now keep in mind, what is current? Current is the amount of charges moving per unit time. So if I bring the magnet very slowly, you see that the bulb is barely glowing, right? And the electrons are very slowly moving. But if I move it faster, then I see that the electrons will move faster, right? But again, it depends upon the field of the magnetic coil, how much it is generating, right? So uh, let's say this is an automatic motion, right? So I turn off the tap, the magnetic field is changing, right? You can see that this is now creating an alternating current because the current moves in one direction, then it moves backwards as well, right? Once the magnetic poles are reversed. I increase the speed of the change in magnetic field. You see that there is a more flux change and the bulb is now growing brighter. If I increase the speed even further, you see that the current change is even farther, and this is how the your bulbs are working, right? So you get 50 hertz current in your house, right? So bulbs are actually turning off and turning on 60 times in 1 second. That is why we cannot detect that, right? Eyes cannot detect it. But if you take your phone camera and point it towards the light, you'll see that the light appears to flicker in your camera, right? Why is that so? Because your camera is able to pick up those 60 hertz which your eyes cannot, right? So the camera will be able to identify those flickering effects. Okay, so this is called the Faraday's law, right? And what does the Faraday law explain over here? That the change in magnetic field induces a change in current in the coil that is attached to it, right? Now this happens even if you have two coils. Now this is one coil in which the current is going in one direction. If I bring it closer, I see that the effect is bringing some effect over here, right? But if I reduce the voltage over here, right, it's the same way, because keep in mind, this is a DC power supply right now, right? If I use an AC power supply, then we're going to have a consistent current. Why is this not giving you a permanent current over here? Reason, because a DC current acts as a bar magnet, right? We want changing magnetic field, and for that we want the power supply to change dramatically. Here we have a fixed power, right? It is a battery that is being used, and batteries provide direct current or a single direction current, right? What is a direct current? A current which is only goes in one direction. You can see that the current is moving in one direction only. If I reduce the voltage, the power becomes less, right? Now if you look at this, if I alternate the power over here, I put this over there, right? Now I am having the same effect that the the changing magnetic field was having, right? But if I keep the voltage fixed in one direction, I don't see any current moving, right? So keep in mind, it's not the value of the current or the movement of the current that causes induction, but the changing magnetic field that causes induction, right? So I have to alternate the magnetic field by reversing the polarity of the current, right, in the battery, by inverting the position of the battery over and over to induce some current. If the current goes in one direction only, there won't be any change, right? Hence, the generators actually require changing magnetic field to do so, right? Now, there are two types of generators for you. One we call as the AC generators, right? The normal generators, and the alternator, we call them, right? The one that is generally used up in the diesel generators, right? And the one that is installed in the car, we call dynamo, right? Dynamo is DC generator and alternator is an AC generator, okay? So we're gonna put it over here, uh, in the box, right, where we were talking about motor effect, right? Right. In the transformer, while we're talking about induction, we'll say that we have two types of generators, right? And generators, number one is an alternator, right? Which is AC generator, we call it. And number two, we have a dynamo, right? And that's a DC generator, right? Again, we're not supposed to know their constructions or their operations. We are just required by AQA stream to only know these two terms, right? What's an alternator? What's a dynamo? Right? It's an AC generator, it's a DC generator. Other than that, the construction, the working is not included in your course. We only have to deal with motors, right? Keep in mind, they don't even have complete motors in your course that I discussed previously in the previous lesson, right? We only have the motor effect, right? And we only talk about the strength of the magnetic field that is there and the factors that were there. We already did that in the, in the previous sessions, okay? That the factors that define, which is voltage, change in magnetic field, and the speed at which that change is happening will define how much voltage is being generated, or how much current is there, or how much force can be created by using this, right? So if I pass more current through this, then the force generated would be stronger. If I have a stronger magnetic field, then the force will be generated, right? And if I apply greater voltages, again resulting in greater current, will result in greater force, right? And if I want to get the generator effect out of it rather than the motor effect, then the applying force or the movement is going to be, the faster I move it, the more the voltage is going to be produced. The slower I move it, the lesser the voltage, which is completely visible over here, right? With the greater force, right, you can see that there's greater of this over here, right? So let me just take this and put it in the notebook as an example, right? So this is an alternator, by the way, right? Why the alternator? Because you can see that the field is changing, right? So and if I reduce the speed over here, right, by reducing the amount of water that is flowing, right, you see that lesser voltages are being produced, okay? So greater the field change or the faster the field change, this is the effect of the force, right? Keep in mind, this is the effect of force that is having, right? So we can say faster flux change or faster change, right? Faster change means more induced voltage, and slower change means less induced voltage, okay? So we want to maximize the voltage being produced by generators or the transformer. We want to have a more flux change, right? We want to increase the flux change. That we can also do by increasing the magnetic field strength, right? The factors that are defined, right? The factors that are there, right, in generation, right? Number one is the applied voltage or the applied magnetic field, right? Either way, if you're using an electromagnet, that's going to be voltage. If you're using a permanent magnet, which is this case, right, applied magnetic field strength, right? How much is the strength? If you're using a weaker magnet, then obviously the induced voltage is going to be less, no matter how fast you're doing it, right? Number two, speed at which the change is happening, right? Speed of change, right? Which we just saw with this diagram, that the speed of change, the greater it is, right? We said that the phi is basically the change in magnetic field. The faster it will change, the faster it will do. And that can be representative of the force we apply, right? The more force we apply, the faster we can move this wheel, right? Which we saw that the greater water was able to rotate this faster, right? So rotating this faster resulted in greater speed, and rotating it lesser or lesser force resulted in lesser speed, lesser flux change, right? So we have less voltage here, and in this case, we had more voltage here, right? As you can tell by the glow of this bulb, right? So this is called the Faraday's law. The Faraday law stated that the voltage generated depends upon the change in the applied magnetic field. Also, if you're using an electromagnet in terms of the coil, right, which we were talking about this other factor over here, right, this double coil, right? So if you look at this, if you have a pickup coil and this, right, so here we said that the greater voltage resulted in greater effect, right? So if I move this faster, the speed defines how much voltage is being there. If I move even slower, then we see that the voltage generated is slower, right? So even though the magnetic field is strong, right, with this electromagnet, right, it's giving a constant magnetic field. But the problem is, if there is no change in magnetic field, then there is nothing that is being generated, right? So a changing magnetic field is required in this case. Okay, so again, let me put this diagram over here. Changing magnetic field only induces current, not a static one, right? A fixed magnetic field does not induce current, as delta B is equal to 0, right? Since we said that the flux change is the change in magnetic field, since the magnetic field is not changing, right, it's a fixed magnetic field, why would there be any glow, right? No voltage over here, right? You can see that the bulb is not glowing, even though the magnetic field is there. It's a very strong magnetic field which is being created, right, in this direction, right? This is going to be the north and this is going to be the south. Since it is not changing, then obviously there is no voltage generated. So in other words, what we stated over here, that it's the speed of change, right? The faster the change is there, the greater the voltage is going to be, right? Then number three factor, which is the number of coils, right? So number three, number of turns of coil. Let's say if you have bigger coil and a smaller coil, right? In this case, let me just move to the other simulation, right? The Faraday law, right? This one. We'll see that which one. Now we have two coils. One has greater and one has lesser number of turns, right? I'm going to show you the field lines. You see, either way, if the field lines cut through it, we generate voltage, right? So if I go through it, then you're going to see more voltage generated, right? So let me attach the voltmeter. You can see the voltmeter reading over here, right? So in this case, when there's a lot of movement, right, the greater voltage is generated when you have more coil. And now you see the voltage is not much, right? For the same speed, it is not able to go to the same voltage. For the same movement, same speed, I'm able to generate more voltages over here, right? Clarified? If I do it slowly, even then it is giving me a lot of voltage, right? But for the smaller coil, no matter how fast or slow I go, the voltages are less, right? So it depends upon the number of turns as well. Clarified? Let me just pick this as well, right? There, right? As an explanation, right? One and the second one as well, right? Let me just take a snapshot of this one. Okay, so there you go. This way you'll have a clarity. Please do try these simulations at your end as well, right? Make sure that you understand these how these things work, right? So we can say over here that less turns means less voltage, right? And more turns mean more voltage. Now keep in mind, in all of these cases, we were using an external magnetic field to do so, right? What a transformer does, that in transformer we have two coils, one is the primary, one is the secondary. Keep in mind, the primary is the one in which you are providing the voltage, right? So what the transformer does, that it's a similar construction, right? Except now we're going to make a complete construction of how the transformer actually looks like, right? So we have an soft iron core, right, which allows us to channel the magnetic field from one coil to the other, right? So this is the soft iron core that I'm making. Just give me a moment to complete the diagram, right? And around this soft iron core, we have two coils, right? So this is our primary coil, right? This is our primary coil, which is going to have lots of turns over here, right? Right, and across, oh dear, yeah, right. And across this, we have, you can say, AC voltage, right? So we're applying AC voltages to this. So I'm just using this as an AC power supply, right? And on the other side, we have the secondary coil, which for now I'm just adding fewer turns, right? And in this case, we're going to attach a voltmeter across these 2 points, right? The voltage across it, or a bulb, right? So what really happens, that the magnetic field around this goes in a very uniform manner across this. We do know that the soft iron actually helps to channelize the magnetic field, right? And why I'm not putting arrows over here, like which way the direction of the magnetic field is going to be there, because it's an AC voltage. So the magnetic field will alter from forward to backward every time there's a change in voltage, right? So if the input voltage is this much, right? Let me draw the input voltages for you, right? So this is going to be your input, right? So if you have the input voltage over here, this is the input voltage, right? And oh dear, I just removed it, right? And if we talk about the output voltage, that's going to be slightly less than this. And why is that so? Because we have lesser number of turns. So we're going to see that the input voltage would be a slightly less. The timing or the frequency is going to be the same, right? We are getting lesser voltages over here. So this is V positive, V negative, right? V positive and V negative. So keep in mind, we have lesser voltage. So this is called a step down transformer, right? As step down means whatever the input voltage are, right? That's the input. The output voltage is going to be slightly less. And why is that happening? So keep in mind, this change in the current produces an alternating magnetic field that goes back and forth, right? Causing lots of change in the magnetic field flux of this coil, right? So the induced voltage is going to be there, right? So voltage would be produced in the secondary coil, right? So this is called, again, which I stated earlier, that this is the primary coil, and the other one is called the secondary coil. Okay, so we get induced voltages in the secondary coil due to alternating current in the primary coil. This device is called a transformer, right? So over here, this is called soft iron core. Okay, and what is the purpose of soft iron core? To channelize magnetic field, right? And this is the only device in the history of mankind that is technically 100% efficient, right? And that is achieved by the use of the soft iron core, right? Because the soft iron core will make sure that all of the magnetic field produced by the primary coil is transferred directly through uh, the secondary coil, right? No magnetic field is lost in this process, right? If we lose some of that magnetic field, if the magnetic field goes out of this, then definitely we will lose some of the energy. But that is the very purpose of using this soft iron core, that it transfers all of this from secondary into this. So let's call these a number of primary turns as ns, right? So the number of turns, these are called turns, right? So these are called primary and secondary turns, right? So we have this, right, the transformation formula, right, the transformation that occurs, right? That is basically the ratio of the turns and the ratio of the voltages are equal. So ns over np is equal to vs over vp. Now what are these terms? I'll explain, right? Ns is basically number of turns in secondary coil. And what is NP? These are number of turns in primary coil. Okay. Vs voltage output at secondary coil, and Vp is voltage output, voltage input at the primary coil. Now keep in mind, as transformers are 100%, right, efficient, or they're considered 100% efficient, for, at least for your exam, right? Their efficiency is 99 or 98%, right? But that is nearly considered as 100%. So for your course, we'll consider, or exam purposes, we'll take 100% efficient transformers, right? So as transformers are 100% efficient, so we can say that the power of input, right, is equal to power at output, right? So in other words, the input power, the total electrical power that you're giving in, should be equal to the total power which is taken out, except there's a drop in the voltage, right? This is step down transformer because we have lesser turns on this side, right? So there are two types of transformers depending upon which number of turns are greater. If the secondary are greater than the primary, then it's a step up transformer, the voltages will go up, right? You'll have less voltage in the input and you'll have greater voltage in the output, but at what cost? It's not possible, since it is 100% efficient. So all the energy that you're giving in should be equal to the energy out. But if the energy in and energy out are equal, why are the voltages changing? So something has to change just to keep the energy constant. And we do know that the electrical power, or electrical power is going to be, right, what is power? Current into voltage. So in other words, the current has to compensate for the voltage. If the voltage goes up, then the current goes down, right, to keep the power constant. Clarified? Using this formula, we can state that for step up or step down, right, we can say that the number of, for the step up, the number of the primary and the secondary are like this, right? For the step up transformer, we've got more number of secondary coil turns than the primary ones, right? So the voltage at the secondary would be greater at the voltage of the primary, but the cost is that the current of the primary would be greater than the current in the secondary. In other words, after transformation, the current will reduce, right? So in other words, if I draw the current and the voltage, right? So we can say that greater voltage at output, right? Lesser current at output, right? And that's the basically the trade-off that we're making over here, right? That the voltage is increased, but as a result, our current is reduced, right? Clarified? So keep in mind, if you trying to attain more voltages, then you'll have to compensate for the current. And if you're trying to get more current, then you'll have to compensate for the voltages, right? So let's say if we talk about step down, and this is what your phone chargers are doing, right? Your phone chargers are working at 220 volts, but your phone requires 3.5 volts. So we use very little current, but your output current or the phone charging current is a lot more, right? I mean, if you know, there are 30-watt chargers out there. 30-watt means at 3.5 volts, we'll just calculate how much of the power is there, right? So first we'll talk about this, right? So in step down transformer, we have more turns in the primary, right? Then the secondary. The voltage in the primary are going to be greater than the secondary one. Again, more turn means more voltages, right? And the current in the secondary would be greater than the primary, right? So keep this mind, that greater voltage at input, or you can say lesser at output, the other way around as well, right? The converse one. And lesser current at input, right? You can, as I said, you can go with the inverse one. Let me just write the inverse statements for this, right? Rather than using input and this, let me match the above one, right? So we'll have lesser voltage at output, since it's the step down one, and we'll have greater current at output, right? Since we're only comparing the outputs of them, this is how we can compare them. Okay. So in other words, if I draw these two ones, right? So more number of turns on the secondary would mean I will have a lot more turns in the secondary, right? This is NS, this is going to be NP. So for the step down one, I'll have more turns in the primary and I'll have fewer turns in the secondary. Clarified? This is what it means to have step up and step down transformers. Usually, when we're transmitting power, we're always transmitting power at higher voltages to reduce the current, because we do understand that the current, using the Ohm's law, V is equal to IR. Keep in mind, if you increase the voltage, you get more current, and as a result, the resistance increases, right? So, what we try to do is that we send in higher voltages and very little amount of current, because we do understand that the current and the voltage are related to one another. The greater the current, the greater the resistance, right? Because I is directly proportional to R using the Ohm's law. We can say that greater current offers faces, right? Greater current faces greater resistance, right? So what we do is that from the grid station to our houses, we get 40,000 volts, right? But your house is operating at 220 volts, right? So how does it work? We use a step down transformer, right? So you can say that the grid sends the voltage at 40,000 volts, right? Or this much, right? And the house uses only 220 volts. So this can only be done using step down transformer, right? Now, same way, your house hold electricity is 220 volts and your phone charger is using 3.5 volts to charge your phone. So that is also achieved using step down transformer, right? So let's now work out some calculations for this, right? I hope we have enough time for the lesson. Okay, no, we actually out of time. Okay, we'll do the numerical calculation in the next lesson, right?